All right, so hello everyone. This is the fourth lesson on avionics, and in this lecture we are going to study the different digital avionic architectures. So we will start with the different generations of architecture, and then we will study about some of the common bus systems or architectures, and then we will also study about the transmission lines, that is the wires which we use to connect different system and subsystem, and also we'll study the optical data bus, right? So these all 3-4 things we are going to study in this lecture. So now in any avionic system there are several subsystems which are connected together to perform a task, right? And to perform the task in the most effective manner, we should interconnect these systems or subsystem. They are not interconnected in a random manner. Instead, we develop an architecture, right? Kind of a blueprint as to how different system or subsystems will be connected, right? So this architecture should be designed in such a manner that you should also keep the future development in mind. Let's say after a few years, if you want to add some more systems or subsystems in this architecture, there should be a possibility to add new systems or subsystems. Okay, so basically your system architecture, avionic system architecture, they are the interconnection of different subsystems. Okay. Now the earlier avionic systems, they were standalone black boxes with separate functions. That is, they had their own sensors, dedicated sensors and processors and display, right? So the first generation, they were disjoint architecture, and mostly they were manual. So the pilot has to look at different panels and display to collect all the data and manually process the information. Now, for example, in this figure, the pilot will have to combine the navigation data and the data received from the radar to decide the best path suitable for the flight. Okay, so these disjoint architecture, they were individual units consisting of their own sensor, processor and display units. Now in older aircrafts or in earlier days, this was feasible, that the pilot would read all the individual panels and collect the information and process it, right? So it was possible in older days because the task performed by the aircraft were simple. But now, with the increase in demand of modern aircraft or in modern aircraft, this architecture is no longer feasible. Okay. Now another first generation architecture, it was centralized architecture. So it's again a development on the previous architecture, disjoint architecture. So in disjoint architecture, each of the units, they were independent or disjoint. In centralized architecture, we had a central computer, right? So all the different subsystems, they were connected to a central computer or to a computer. Okay. And this computer would then process all the data from different sensors or subsystems. However, this architecture, it requires lots of conversion, that is from digital to analog and analog to digital conversion for interfacing with the computer. Okay, so the centralized architecture had simple design and softwares can be written easily, but they need long data bus or wires to connect all the subsystem to a single computer. Okay, and also the software was not very versatile, you can say. So different offer, so they don't offer much flexibility. Also, they require different conversion techniques, as I mentioned, because the first, it's a development from the previous architecture. So the previous architecture, they were individual, right? So to integrate all those individual component, you require lots of conversion, okay, to interface it with a single computer. So again, you had some limitations. The second generation architecture, the first architecture was federated architecture. So federated means join or join together. Okay, so this word federated, it means joined together. Okay, so in second generation federated architecture, each system, they act independently, but they are united or they are loosely coupled. So data conversion, it occurs at the system level instead of at the computer. Okay, as in the case of centralized architecture, right? So data is sent in digital form. Okay, so basically in federated architecture, each of the subsystems would convert whatever data into digital format, and this digital signal is then sent to the centralized computer. Okay, so still the processing is happening at the central computer in case of federated architecture, right? And they use time division multiple access, that is TDMA, for data transmission. So in time division multiplexing or time division multiple access, TDMA, each system or subsystem, they are allotted a time frame during which only that system can transmit its data. Okay, so this way multiple systems can share the same data bus and obviously you can reduce the wiring in the aircraft. So this architecture use standardized protocol to connect different components or different systems, so which allows interchangeability of equipment. That means if you want to change that equipment with an advanced one, you can easily just connect it. Now, some of the additional advantages for this federated architecture, it includes your fault containment. That is, if a failure or fault occurs, the fault data is not sent to the processor. That is, if any fault or failure it happens, the faulty data will not be sent to the processor or to the centralized computer, right? So even though this architecture, it provides several advantages over the previous generation, but still it is unable to utilize the resources effectively. So after the federated architecture, we had another architecture called the distributed architecture, right? So the second generation distributed architecture, it uses multiple processors, right, instead of a centralized processor. So these processors, they will process the data in real time according to the mission and system status. Okay, so these processors, they will process the data there itself in the or within the subsystem itself, according to whatever is your mission and whatever is the status of the system. And now the processed data is sent on the data bus. Okay, so this architecture, it reduces the use of data bus. So previously you have to send the data itself to the computer. So you would need more number of wires or data buses. Okay, data buses are basically, you can say they are wires. Okay, but now to send the processed data, you can now reduce the number of data buses. Okay, so this architecture, it reduces the use of data bus or wires, which further reduces the operation cost of the aircraft, and also it improves the response time. Okay, because now you are sending the processed data to your computer, so it will take less time to to process that data and produce whatever information the pilot would need. Okay, so this distributed architecture is used in modern avionics systems. Okay, the next architecture is your hierarchical architecture. So hierarchical architecture are derived from the previous federated architecture, and they are based on tree topology. Okay, Now in this architecture, the critical functions, they are placed on a separate data bus, and non-critical functions, they are placed on another data bus. Okay, so critical functions and non-critical functions, they are placed on separate data buses. So this way, failure in non-critical part of the network will not affect the critical operations of the aircraft. Okay. And the communication between the subsystem of a particular group are confined to a particular group. So the communication between the subsystems, they are confined to its own group, right? For example, your subsystem monitoring or controlling the engine of the aircraft. So it has no concern with the navigation system. Okay, so they cannot communicate with each other. However, let's say the fuel injection system of the aircraft, they can communicate with the subsystem monitoring the engine of the aircraft, right? So the subsystem belonging to a particular group, they can only communicate with each other, right? So this way the load on the main data bus is reduced, right? So this reduces the load on the main data bus. Okay. And most of the military avionics today, they are based on this hierarchical architecture. Now for the third generation avionics system, more emphasis was put on standardization, right? Standardization and optimizing the system to make it suitable and mission effective and reducing the overall cost of the aircraft. Now one of the architecture, third generation architecture, is your Pave Pillar. So Pave Pillar architecture is a US Air Force program to define the requirements and avionic architecture mainly for fighter aircraft or military aircraft. Okay. And in this Pave Pillar architecture, the key emphasis was to increase the information fusion and higher level of complexity of software. That means more advanced softwares and more effective softwares were used. And then standardization to simplify maintenance. Okay. Reduce the cost and include capability to use emerging technology or new technology in the future, right? So from third generation or onwards, there was very less of system alteration or physical system alteration. Instead, more emphasis was on developing high-end or more effective softwares and standardization, so that you can plug in different or new technologies into your existing architecture. Okay. Now, electrical data bus system. So, series digital data bus system in avionics are mainly classified on the basis of their speed or data transmission rate. So we have the low speed data bus with a typical transmission rate of or between 1 and 2 Mbps, and the two most common bus systems, they are your military standard 1553 and ARINC, or Aeronautical Radio Incorporated, which is a company or a industry, and it has a transmission rate of 2 Mbps. Okay. The high speed data bus system, something like LTPB, linear token passing bus, and high speed ring bus, HSRB, they have a transmission data rate of around 50 to 100 Mbps. Okay. Now in our class, or in today's class, we are going to study only the low speed system in detail. Right? So we are going to study both of these systems. So let us discuss about the first one, that is military standard 1553. So 1553 bus system is a US military standard which uses time division multiplexing to transmit and receive data between multiple sources and multiple sync. So multiple sources means your transmitter, you have your sensors, and then several other systems or subsystems which are transmitting or which are the source of that data. Okay. And multiple sync, you can have a display or a processor, or again you can share that data with other subsystem. So those are your multiple sync. Okay. So it is widely used in military aircrafts in many countries, and not only in military aircrafts, but this bus system is also used in naval ships and submarines and battle tanks. Okay. Now this system is half duplex. That is, only one system or subsystem can either transmit or receive the data at a time. That is, at a particular time, you can either transmit or receive the data. One very common example of half duplex system is your walkie-talkie, right? Most of the police and other, people, they use walkie-talkie. So in walkie-talkie, you can either transmit or receive at a particular time. Okay, so this military standard 1553 bus system is a half duplex system. Okay. Now this 1553 bus system it has these elements or these components. So you have the bus controller, you have a remote terminal, and then you have monitoring terminal and transmission medium. So transmission medium, that is your wire or data bus. Okay. So the system is a command response system. That is, all data transmissions, they are carried out under the control of bus controller. That is, for transmission you would need a command from bus controller. Okay. Now if you look at the figure in the slide, so each subsystem, they are connected to the buses through a remote terminal. Okay, they are not directly connected to your bus. Instead, in between you have a remote terminal, RT. Okay. Now data can only be transmitted from one remote terminal to another remote terminal only after the command from bus controller. Okay. So for transmission or reception, the bus controller will give a command to your remote terminal. Only after that you can, or your subsystem can, transmit or receive the data. Okay. Now the operation of the data bus system is such that the information transmitted by the remote terminal is addressed to more than one remote terminals. That is, all the remote terminals. So you would have multiple remote terminals. So this is your data bus. You will have your bus terminal or bus controller and multiple remote terminals connected to different subsystems like that. Okay. So the information from your bus controller, it is transmitted to all the remote terminals. This is called as broadcasting. Okay. So the transmitted information will be available to all the remote terminal which are connected on the data bus. But the data, it can only be accessed by a particular remote terminal, right, which is being addressed. Okay. Data can only be accessed by the addressed remote terminal. Okay. Although data is being broadcasted to all the remote terminal, but it can be accessed by only a particular remote terminal. which is being addressed. Okay. Now, to specify this address, the data is transmitted in a particular format, which is called as word. Okay. So in 1553 bus system, there are 3 types of word that are used for data transfer. The first is your command word, which has 6 separate fields. Okay. So you have the synchronous bit, then you have the terminal address, and then transmission or reception, that is whether the data will be transmitted or received by the remote terminal. And then you have sub address or mode, and the data word count, that is the number of bits in your data. Okay. Now the synchronous bit for, if we look at the synchronous bit for the command word, it is high for 1.5 bit time. Okay, 1.5 bit time, and it is low for 1.5 bit time. Okay. And 1.5 bit time, it is low. It is quite specific, the synchronous bit. Okay, so what happens is all the remote terminal which are connected on the data bus, they will look for this type of a synchronous signal, and only after it receives this type of a signal, the remote terminal will read rest of the bits or information. Okay. Now, depending on the terminal address in the command word, the corresponding remote terminal will send its status, okay, using the status word. So the status word, it is the first word of response from a remote terminal to the bus controller. Okay, so it provides the information about the status of the remote terminal, that is, if it is busy or ready to transmit. So your status word also have the information about the word, data word, that is number of bits in the data which is to be transmitted. And also it has 4 fields. So you have the synchronous bit, and then you have the terminal address, and you have the status field, and a parity bit. Okay, so you can send a maximum of 16 bit at a time. Okay, so if you look at the data word, you can send a maximum of 16 bit of data at a time using data word. The synchronous signal, if you look at the synchronous signal, it is just the inverse of command and status word. Okay, so it is low for 1.5 bit time and then high for another 1.5 bit time. Okay, and the most significant bit is transmitted immediately after the synchronous bit. So the first bit after your synchronous bit will be your most significant bit. Okay, and this parity bit, okay, this P, it stands for parity. Parity bit. Okay, so if you look at all the words, command word, data word and status word, the parity bit is always high or 1. Okay, and it is used as an indicator that if any errors occur during the transmission. Okay, let's say if you are transmitting the data and your data somehow get lost, and at the receiver end you are receiving all zeros, so even this parity bit will be 0. So that way the receiver will understand, or it will identify that all my data has been lost because parity is 0. Okay, so it will identify. So it will ask the transmitter to send the data again. Okay, if it is high, then the data has been received properly. So parity bit, it is used to identify any error during transmission. Okay, so it is used to identify error during transmission. Okay, and it is always high or 1. Okay, now these are the specification of military standard 1553 bus system. So data rate is 1 Mbps. The word length is 20 bits, and the maximum transmission rate is 50,000 words per second, and the maximum number of terminals it can support is 31. So you can connect maximum 31 number of remote terminal and your subsystem. Okay, so you can go through all the specifications. Now the next type of bus system is called as your ARINC in short, and that is your Aeronautical Radio Incorporated. So as I mentioned, this is a non-profit organization in the US which defines system and equipment specification in terms of functional requirement, performance and accuracy. So it's kind of a non-profit organization which defines the specification, okay, based on the task or the mission and the accuracy you need. Now military standard 1553, they had some limitations. Okay, so I've mentioned them here. So for example, for a military standard 1553 bus system, you need a remote terminal. Okay, so every subsystem was connected to a remote terminal, which was then connected to the bus. Okay, and if that remote terminal, if it fails, then it would compromise that particular subsystem. Okay, that subsystem will be completely disconnected from the data bus if the remote terminal fails. Okay, so that was one of the limitation of your 1553 bus system. Another thing with 1553 bus system was any changes in the bus controller software would require certification. Okay, so as a process of standardization, every component or every software that you use in the avionics system, they require some certification. Okay, so in this military standard 1553, you would need frequent certifications. Okay, so therefore, because of these limitations, ARINC 429 standard was adopted. Okay, now this ARINC 429 is a point-to-point bus system. That is, it has a direct connection between your transmitter and receiver, one or more receivers. Now it is a simplex data bus. That is, data can flow in only one direction. That is from the transmitter to the receivers. Okay, and 429 bus system, it can support a maximum of 20 receiver. Okay, now there are no physical addressing like in military standard 1553 bus system. That is, you don't have any bus controller. So in ARINC, instead of any physical addressing, we use something called as identifier or label. Okay, so we use an identifier or label in the word. So ARINC also have a word format. Okay, so in the word format of ARINC, we use a field which contains the label for the receiver. Okay, so if you want to transmit or send the data to a particular receiver, we use a certain bits to label that receiver. Okay, now it can operate at two alternative data rates, which are 100 kbps and 12 to 14 kbps. Okay, and there are no bus controller in the data bus, and it has direct coupling. So instead of having a remote terminal and a bus controller, as in the case of 1553 bus system, there is a direct coupling between the transmitter and the receiver. Okay, Now, a slight advancement in ARINC bus system is your ARINC 629. So this 629 bus system, it is a bi-directional data bus. Okay, so it is again half duplex system. That is, transmission and reception is possible, but only one at a time. Okay, the data rate is higher than the previous version, that is 429. Okay, and the data rate is 2 Mbps, which is much higher than your 429 bus system. And also we can connect up to 120 receivers in 629 bus architecture, and it is a multiplex system with multiple transmitter and multiple receiver. So all these terminals, they can be either transmitter or receiver. Okay, so it is a multiplex system. You can connect multiple transmitters and receivers. So basically in 629 bus system, it works on the principle of flexible time allotment to each of these terminals. Okay, and they use something called as token. So for transmitting or receiving whatever data, each terminal will require a token. Okay, and once it has transmitted its data, the token is then passed to the next terminal. So like that, one by one, each of the terminal will either transmit or receive the data. Okay, and obviously fixed time is allotted to each of the terminal. Okay, now coming on to the transmission line or the data buses which we use. So they are basically your transmission lines or wires. So a transmission line mainly provides a medium for the signal to propagate. Okay, now they could be used for short distance transmission or long distance transmission, and there is an entire theory about it, but we are not going to go into details. Now for transmission of electrical signal, a pair of wire, a positive and a negative terminal, or a pair or two number of wires is just sufficient. Okay, using two wires you can transmit or receive any electrical signal. Now these metal wires will have some resistance, inductance and capacitance. So we can model the transmission line by this type of a RLC circuit. Okay. However, for short distance transmission, which is less than 80 kilometers. Now in the case of aircrafts, the maximum distance you would need for transmission is around hundreds of meters. Okay, so for short distance transmission, this capacitance is very low, and you can avoid the capacitance, the effect of capacitance, right? So basically this RLC model of your transmission line, you can reduce it to RL. Okay, resistance and inductance connected in series. Okay. Now, because of this impedance, so you have resistance and inductance. So together, it is called as impedance. So because of this impedance of the wire, when current or electrical energy flow through this wire, the wire will get heated and lose some energy. Also, these transmission lines or simple wires are affected by the electromagnetic interference. Okay, so which disturbs the signal which the wires are carrying. Okay, therefore, to use a transmission line in an aircraft, it should follow two characteristics. The first characteristic is your transmission line should be able to transmit signal over a wide range of frequency with minimum losses. Okay. So to reduce transmission loss, sometime gold or silver plated wires are also used, because gold and silver they are one of the best conductor of electricity. And to reduce the heat loss, the metal wires, they are covered with a dielectric material. Okay, you might have seen the wires. You have some plastic type coating on the wires. Okay, to reduce the heat loss. Okay, so you use Teflon or polyethylene coating on the metal wires to reduce the heat loss. Now, the second characteristic is that your transmission line should provide immunity from signal egress and ingress. That means it should stop any outside signal to enter the transmission line and affect the signal, and any signal which is being transmitted on those wires to leak out. Egress and ingress. Ingress means from outside. Any signal should not affect my signal which is being carried by the transmission line, and whatever signal is being carried, that should also not leak out or get lost. Okay, so these are the two requirements or characteristic of your transmission line. Now, in an aircraft, we generally use twisted pair or co-axial cables as a transmission line for transmitting your electrical signal. Nowadays, optical fibers are becoming more popular, but for electrical signals, you would need to convert them into optical signal, and then you can use optical fibers also for transmission. We will study about them in a short while in today's class, but for now let us first discuss about the twisted pair cable. Now, the benefit of twisting two pairs or two parallel wires. So twisted pair, basically you have two parallel wires which are twisted together. Okay, you twist them together. So the benefit of twisting two parallel wires is to reduce electromagnetic interference. Okay, as I mentioned before, that when alternating current flows through a wire, electromagnetic field is produced. So whenever you have any conducting wire and you connect it to alternating current, so if it is flowing through this wire, some electromagnetic field will be produced. Okay, and if you have a second wire close to the first wire, this electromagnetic interference, it will be induced in the second wire also. Something like this here. This is a much better and clear picture. So if you have some alternating current flowing in this wire, some electromagnetic field is produced, which then induced into the second wire. Okay. Now, as a result of this electromagnetic field linking with the second wire, some current will be produced in the second wire. Okay. And this current will interfere with the signal. So your signal will also be in form of electrical current in the wire. So this current and your data current, let me call it data current, will interfere with each other, and ultimately it will spoil, or it will distort your signal, your data signal. Okay, so that's how your electromagnetic interference, it happens in parallel wire. Now if you twist them, in case of twisted pair, what happens is, if you twist them, you will have electromagnetic interference in opposing direction, or in the opposite direction. Okay, so in the two wires, one electromagnetic field will be in clockwise direction and another one will be in anti-clockwise direction, and they will ultimately cancel each other. So as a result of this, there will be no electromagnetic interference in the twisted pair cable. Okay, so that's how we avoid electromagnetic interference from the between the two wires. Okay, now we have two types of twisted pair cables. You have, one is your unshielded twisted pair, and you have your shielded twisted pair. So in unshielded twisted pair, it is similar to your LAN cables. Okay, you use it for connecting internet to your computer, those LAN cables. Okay, you might have seen this type of a wire. So they are simple, like different pairs of wire which are then twisted together. Okay, so they would protect any electromagnetic interference within the wire, but if some external electromagnetic field is around that wire, it will not protect your data. Okay, unshielded twisted pair cannot protect data from external electromagnetic interference. Okay, now obviously in an aircraft you have so many wires, so many electronic equipments, right? And so you would have quite large amount of electromagnetic fields in the aircraft. Okay, so to protect your data from external electromagnetic field, we use shielded twisted pair. So in shielded twisted pair, you have a mesh, a wire mesh, okay, along with your twisted pair. So around it, you have a wire mesh. So any external electromagnetic interference will first link with this wire mesh and produce any current in that wire mesh. Okay, and this wire mesh is then connected to ground. Okay, so any current which is being produced by the external electromagnetic interference will be grounded. Okay, so it will kind of protect your data from external electromagnetic interference. Okay, the next type of transmission line is your coaxial cable. So again, you might have seen the coaxial cable. Okay, so the coaxial cable, it has a copper mesh and a copper wire. So your copper wire, it will carry your data, okay, whatever you are transmitting. And this copper mesh, so again it is used to protect data from external electromagnetic interference. Okay, so if any external electromagnetic interference is around this wire, so that will induce a current in the outer mesh or in the copper mesh, and this copper mesh again, it is then connected to ground. Okay, so any interfering current is then grounded. Okay, so this copper mesh and your copper wire, they are separated by an insulation. Okay, so this coaxial cable, they are used to carry high frequency signal with low losses. Okay, and I think the transmission rate in coaxial cable is also high in comparison to your twisted pair cable. Okay, but they are a little expensive and hard to install. Okay, and because of all these copper mesh and insulation, these coaxial cables, they are slightly heavier in comparison to twisted pair cables. So again, that would increase the weight of the aircraft. So in most aircraft, we generally use shielded twisted pair cables for long transmission, and sometimes we also use coaxial cable, but shorter lengths of coaxial cables are used, not very long. Now, before discussing about the optical fiber, or optical data bus. Let me quickly remind you some of the basic concepts of light transmission. Okay. So according to Snell's law, when a light travels from a denser to a rarer medium. Okay, whenever a light travels from a denser to a rarer medium, it will bend. Okay, and that bending of light, we call it refraction. Okay, refraction. Right, now the bending or refracting angle R, it depends on the refractive index of the two medium, that is N1 and N2, and the angle of incidence. Okay, so refractive index, basically it tells us the optical density of a medium, that is how fast the light can propagate in that medium. Okay. Now the relation between the angle of incidence, refraction, and the refractive index of the two medium, it is given by your Snell's law, by this equation. So if we keep on increasing, as you can see in this animation, if we keep on increasing the angle of incidence, a situation will come when the refracted ray will travel parallel. You can see it, right? Refracted ray will travel parallel to the interface between the two medium for a particular angle of incidence. Okay, so if we increase the angle of incidence, the ray of light will bend more, or the refracting angle will also increase. Right, so if we keep on increasing the angle of incidence, there will be a situation that the ray of light will travel parallel to the interface between the two medium. Okay, so that particular value of angle of incidence, it is called as your critical angle. Okay. So if the angle of incidence is equal to critical angle, the refracted ray travel parallel parallel to the interface, between two medium. Okay, this one. Okay, now if we further increase the angle of incidence greater than this critical angle, the refracted ray or the ray of light, it will reflect back into the same medium. Okay, and that is called as total internal reflection. Okay, so for angle of incidence greater than critical angle, total internal reflection, or in short TIR, will occur. Right, so the ray of light will be reflected back into the same medium, and with almost 99.9% of the light will be reflected back in the same medium. Okay. Now these optical fiber or optical data buses, they work on the principle of total internal reflection. Okay. So these optical fibers, they are basically waveguides, okay, consisting of a glass cylinder, okay, with two layers. So mainly this glass cylinder or this optical fiber, it has two layers, two main or important layers. Those are your core and cladding. Okay. Of course, you have other protective layers because your optical fiber, they are made out of glass, right? And they are very thin in micrometers. Okay, so you need some protective layer to protect your glass optical fiber, and you have some outer jacket to protect it from environmental degradation, something like sun and rain. Okay, so you have some kind of a plastic coating, that is your outer jacket. Now the refractive index of the core is slightly greater than that of the cladding. Okay, so the refractive index of the core is greater than that of the cladding. Okay, and the ray of light is incident into the core. Okay, the ray of light is incident into the core at an angle greater than critical angle. Okay, so these two things allow the light to propagate inside the core by total internal reflection. For total internal reflection, you need two things. The refractive index of medium 1 should be greater than the refractive index of the second medium, and the angle of incidence of the light should be greater than critical angle. Okay, so both these things are maintained in this optical fiber. The core, it has refractive index greater than cladding, and the angle of incidence is greater than critical angle. So the light, as you can see in this animation, the light would propagate by multiple total internal reflection throughout the length of the optical fiber. Okay, so these optical fibers, they are immune to electromagnetic interference, because electromagnetic interference, it happens in electrical signal, and now we are transmitting the data by using light. Okay, so there will be almost no electromagnetic interference, and again you are using light, so the data transmission rate will also be very high. Okay, now the optical fibers, they are of two types. We have single mode optical fiber and multi-mode optical fibers. Now the key difference between the two is the core diameter. So for single mode optical fiber, the core diameter is around 5 to 10 micrometers. Whereas for multi-mode optical fiber, the core diameter is larger. Okay, that is 50 to 100 micrometers. The cladding diameter in both the case is 125 micrometers in both. Okay, the key difference is in the diameter of the core. Now, according to Snell's law, the angle of incidence should be greater than critical angle for total internal reflection. Okay, but we don't have any specific value. Only thing is angle of incidence should be greater than critical angle. So we can have a range of angle of incidences which are greater than critical angle. Okay. Right. Now, in the case of single mode optical fiber, since the diameter of the core is very small, so it would only allow one angle of incidence for the light to propagate by total internal reflection. So in single mode fiber, since the core diameter is small, the light can only follow a single path or single angle of incidence. Okay. However, in the case of multi-mode optical fiber, since your core diameter is larger, so you can have multiple angle of incidences, and all those light will propagate by total internal reflection. You can see that, kind of see that in the animation here. Okay, so basically multi-mode optical fiber will allow multiple rays of light to propagate within the same cable or same optical data bus. So kind of you can multiplex different system or use a single optical data bus to transmit multiple data. Yeah. Now, based on this waveguide parameter, so we have the formula here. So based on this waveguide parameter, we can decide whether an optical fiber is a single mode or a multi-mode optical fiber. So this waveguide parameter, it depends on the operating wavelength, the core radius, okay, radius, and delta. Okay, so delta is your fractional index change. Fractional index change. Okay. Right. And if it is your waveguide parameter is greater than 2.4048, then it is, sorry, if it is less than 2.4048, then your optical fiber is a single mode. And if it is greater than this value, it will be a multi-mode optical fiber. Okay. So, it is possible to adapt existing electrical connectors to use multi-mode optical fibers in your avionics system, right? By designing your system accordingly. So we can use LED to convert the electrical signal into optical, and then we can use photo detector to convert your light signal back into electrical, right? So it is quite possible now transmit your data in optical format or optical form using optical fiber or optical data buses. Now, obviously, as I mentioned, some of the advantages, the optical fiber, they provide a very high data rate that is greater than 10 gigabytes per second, and it is insensitive to electromagnetic interference. Then electrical isolation. So basically it is insensitive or not affected by electromagnetic interference, so it is electrically isolated. So it is quite ideal or perfect for using in an aircraft, because you have so many electrical equipments which would produce some electromagnetic field and which could cause interference if you are using metal wires. Okay, so optical fibers, they can provide electrical isolation. Then low crosstalk and low power dissipation or losses, and obviously these are very fine, very thin optical cables, so they are very less in weight, so you can reduce the weight and volume requirement. Okay, so the dimension is maximum around 125 micrometer for single mode or multi-mode optical fiber. So they are very thin wires or optical wires, you can say, and they are very light in weight. Okay, now I have included two of numericals here. They are quite simple and they are based, one of them is based on Snell's law and the other one is based on the waveguide parameter. So I'll just quickly go through this numerical. So the first numerical, it says that light passes from air to an unknown medium at an angle. So angle of incidence, it is given as 43 degree, and the angle of reflection, it is given as 28 degree. R is given as 28 degree. Okay, now since your first medium is air, and air, it has a refractive index of 1. Okay, and we have to find that what is the index of refraction of the unknown medium. That is, we have to find the refractive index of the second medium. So we can straight away use Snell's law, that is N1 sine I is equal to N2 sine R. Okay, so I've solved it in the next slide. So if we put in all the values, N1 is 1, angle of incidence is 43 degree, angle of reflection is 28 degree. So we can calculate N2. Okay, and according to my calculation, it comes out to be 1.453. Okay, now refractive index, it is a unitless quantity. Okay, so it will not have any units. Okay, now obviously based on Snell's law, you can have multiple questions, maybe to calculate angle of incidence, angle of reflection, or the refractive index. Okay, so based on this formula, you can get a numerical. Now the next numerical, it is based on the waveguide parameter. So let's read the question. So question says an optical fiber has a core diameter. Okay, so core diameter of 6 micrometer and material with a refractive index of 1.55, and its cladding material has a refractive index. So this is I can call it as NC or N1. I can call it as N1. That is the refractive index of core. It is 1.55, and refractive index of cladding N2, it is 1.5. Okay. The light is launched into it in air. Okay, and we have to calculate the fractional index delta, fractional index change delta, and also determine if it is a single or a multi-mode optical fiber. If the operating wavelength, it is 1550 nanometers. Okay, so we can use these two formulas. So fractional index change delta is N1 minus N2 divided by N1, and waveguide parameter is given by this formula. Okay, so let us look at the solution. So we are given with the core diameter. It is given in micrometers, so I've converted it into meters. The refractive index of core and cladding is given, and the operating wavelength is given. So operating wavelength is again in nanometers. Okay, so I've multiplied it with 10 to the power 9, converted it into meters. Okay, then we have to find those two values. So let's first find the fractional index. So again, you can simply substitute N1, N2 in the formula, and I got this value to be 0.03. Okay, again it is unit less. Okay, because all these N1 and N2, the refractive index, are unit less quantities, so your delta will also be unitless. And then we can use value of delta here and all the other values in this formula and calculate the wave parameter. So wave parameter, it comes out to be 9.58, right? And since we have to decide if it is a single mode or multi-mode, so this waveguide parameter, it is greater than 2.4048. So it is a multi-mode fiber, multi-mode optical fiber. Okay, so similar type of questions you can practice. I think some of them I've mentioned in the tutorial. Okay, so you can try out those questions. So this is all that I wanted to discuss in today's lecture.